a classical picture for spontaneous emission. Okay, consider a Hertzian dipole. When the Hertzian dipole emit an electromagnetic wave, okay. They emit electromagnetic wave, go to far field. So the electromagnetic wave will emit. When they emit, they have the reaction force. They have the reaction force to this dipole. We call this a reaction. It's a radiation reaction. Radiation reaction or radiation, they have some force, reaction force to this dipole. It's easy to understand. Okay, so finally, the dipole will decay. Okay. They satisfy the Lorentz sheaf spectral. This is the Gaussian equation. This gamma 0 R dot term, okay, because R dot is just partial R by T. Okay, this is Lorentz sheaf. This is omega 0. It means the dipole will decay. Okay. Okay, from classical theory, the dipole will decay. Because it really is an electromagnetic wave, it has a radiation damping. Okay, it has radiation damping. The gamma 0 is the radiation damping rate. This gamma 0 term, this term is damping. And the bandwidth is also equal to the gamma 0. This is 1 over 2. This is bandwidth. The gamma 0 is just, we call it a classical decay rate. But from classical view, you cannot explain some phenomena well, especially for some atom, molecule, quantum dot. When they are spontaneous emit photon in vacuum, okay, that means in a dark environment without any EM field. When these spontaneous emit photons, they will come to rest, okay, according to the classical theory. Now, from classical theory, they will come to rest. But it does not agree with the real-world physical phenomenon or real-world physical effect. Okay. So here, the basic idea is called a fluctuation dissipation theorem. To understand this phenomenon, I give a short introduction to this theorem. Okay. They said, okay, if a dipole, they emit wave, okay, to the free space, simultaneously, the EM wave from the vacuum also return back, react on this dipole. The two processes will balance each other at thermal equilibrium. This is and this vacuum field, this vacuum fluctuation field, okay, E here is similar to noise. It has an expectation value 0, but their variation is not equal to 0. This field is the vacuum fluctuation field. Okay. So they are balanced each other. When they emit photon, they also receive photon. Okay. Similar vacuum get energy from this emission. They also give energy to this dipole. The two processes are equivalent to each other. Okay. This is called a fluctuation dissipation theorem. Fluctuation dissipation theorem says if there is state. Give back to you. It's okay. Okay. If there is still shine, okay. If there is a process dissipating energy, okay, if there's a process dissipating energy, there will be another reverse process to compensate the dissipated energy. The reverse process typically is a fluctuate field. I give 3 examples. In last lecture, I gave 3 examples. One example is just Johnson noise. Johnson noise is found by the Nyquist. Okay. It's same Nyquist with the Shannon Nyquist sampling server. Okay. So Nyquist at that time they understand this Johnson noise. They said it is a resistance. Okay. This resistance they absorb the electromagnetic wave. Okay. And they produce a heat. They have KBT here. Then they also emit the electromagnetic wave similar to black body. They balance each other. Okay. So the fluctuation current, expectation value of current, or R, is a power, just KBT, classical, just KBT dF. So in a broadband noise frequency, just KBT OB. It's a famous equation every engineer should know. Okay, this is just to the fluctuation dissipation theorem. Okay, the resistance dissipate energy. Okay, they dissipate energy. Okay, but they also emit the electromagnetic wave to free space. They are balanced. They absorb the wave, the emitted wave. Okay, here is Johnson noise. Another is called Brownian motion. Okay, I think this is by the Einstein. It started as Brownian motion. Brownian motion. Consider water. This is water. They have small molecules. They are randomly move very fast. Okay. When the molecule move, they have friction force. Right? They have a drag. If have the friction force, intuitively you think that the molecule will stop because they have friction force, right? Like some, you consider some objects, they have some friction force, they go to a very smooth ground, they move a short distance and stop. Why they do not stop? They still go very fast. Because this friction produce heat, increase the temperature, and the KBT here, it produces, the KBT also increase the kinetic energy, V. Okay, it's a kinetic energy. So this is also fluctuation dissipation theorem. Okay, friction force, they will make this movement of this particle slower and slower, but not because they have temperature. This temperature also increase the kinetic energy of this molecule. So you can see the molecule move very fast, cannot stop. Okay. The two is to be balanced, KBT equal to 12m Vd squared. Okay, the velocity here is fluctuate. Okay, it's a random process. We call Brownian motion. The third is just a black body radiation. At thermal equilibrium, some materials absorb EM wave. Okay, they also emit EM wave. At thermal equilibrium, the emission rate equal to the absorption rate. Okay. For black body, is equal to 1. So black body is a very good absorber. It's also perfect emitter. The two processes are detail balanced. They balance each other. This all the phenomenon, even they call it it's by the dual SAM theory, they call it a fluctuation dissipation theory. Okay. So So fluctuation dissipation theory said at thermal equilibrium, the physical process obeys the fluctuation dissipation theory. When there's a process dissipate energy, there's a reverse process related to thermal or quantum fluctuation for compensated energy. There are two processes obey the detailed balance. Okay. This is the fluctuation dissipation theory. This is from the classical theory. We get some phenomena we cannot explain, so we should explain use a quantum optic view. Okay. So this is just a thinking. In last lecture, I also talked about this very controversial theory about this dissipate power from a dipole. Okay, it's a classical dipole. Consider a dipole. This object around this dipole. It can be metallic sphere. This is a dipole. This dipole, in my case, is atoms, molecules, and quantum dots. This is the emitter, also absorber. The two processes are balance each other. Okay. So I have a very interesting conclusion. They said, oh, the emission power, it has a closed surface S, as N here. The 1 over 2 E cross H conjugate real part dot ds. This is the radiation power. Okay, this is the radiation power. I plus absorption power by the sphere is 1 over 2 sigma E square dV. Okay, this is similar to radiative. Okay, this is absorptive. Okay, so who gives this source? It's dipole. Okay, it's just dipole source J dot E here, 1 over 2. 1 over 2. It's a minus. 1 over 2 dV. From this equation, we know that from this equation, it's important to think that it's a real part. It's also real part. The source here is for active material. This is important. It's for active material. Okay, this is something source. For this source, they produce energy. One part of energy was absorbed by the metallic sphere. This is a non-radiative part. Another radiative into the far field. Okay, so just 1 over 2 real part E cross H dot ds. This is the radiative part and absorptive part. Someone call non-radiative. And this is the total energy. The total energy provided by this source. This is active material. This is very important. Okay, from a very simple relation, the J here is equal to minus I omega mu. Mu here is the dipole momentum. And delta R go R0. This is the first thing dipole. And E field is just omega square mu, and the dielectric Green function in homogeneous space R0, and mu. Okay. This is dielectric Green function in homogeneous space. In homogeneous space. We go back to this case. I mean, dielectric Green function is just in the G in homogeneous dielectric Green function equal to G free space plus G scatter. Okay. I mean this wave that goes to the metallic field. The metallic field will produce some polarization current. This is a polarization current. Then scatter again to here. This is a scatter field. This is scatter field. So here the field can be enhanced. Okay, if without this metallic sphere, the incident field just from the dipole itself. But now, if I put a metallic sphere so very close to this dipole, the scatter field from metallic sphere also can enhance the field at this point. According to this equation, this is a very magic equation. Because J is Hertzian dipole, okay? It has some selectivity. So only the E field at this point and this R0 point contribute to this volume integral. Okay, only the R equal to R0 can contribute to this. So finally, we get this very famous equation. It has some constant C. I just ignore them. N is the polarization direction, N polarization direction, and dielectric Green function in homogeneous space, and NP here. Okay, this is something we get. And the imaginary part, sorry. This is the imaginary part. There's a reason why they have imaginary Green function because it has I here. Okay, they have I. This is initially they had real part because they have real part, but they have I here. So I finally we get imaginary Green function. Okay, so this is a very paradox. They said, oh, if you want to increase the emission power, across to this closed surface, the total emission power, it's just necessary to increase the field at this point, okay, or imaginary power of this field. Green function similar to field, this point, just one point. Okay. This is a very paradox. This is quite different from the traditional antenna theory. Okay, because traditional antenna theory, you give a power. This power is an input power. Then this power will go out. They call output power. The output power should be input power because the efficiency of antenna should be smaller than 100%. Okay. But here, why there has no paradox here? Because when we think about what is the source of the antenna, okay, what is the source? What's the definition for source? So source is active material. This is very important. For antenna, what is the source? Okay, I draw the antenna, classical antenna picture to see what happened. If it is classical antenna, it's dipole antenna. Typically, they should connect to some coaxial cable, right? Coaxial cable. This coaxial cable will do some vector net analysis, VNN, right? They have source within. Okay. They have source within. This source typically has PN junction. So in this equation, the source is active material. Everything are passive. For antenna, everything are passive, right? This is just metal. Coaxial cable also a metal. So everything are passive. When you go deeper, go further, the semiconductor material is source. This is active. Okay. If you increase the E field, can indeed increase the absorption of this material. And the EM field are produced by the absorption of the material. They can increase the total emission power. Okay, so this is a key point. This is the key point. Okay. So from this equation, you said, if you're because I said this point, this Hertzian dipole point is a quantum dot, atom or molecule. Okay. You increase the E field here, you just increase absorption of this material. Then they can emit more power because absorption and emission are balanced. Okay, in spontaneous regime. Okay, so you just enhance the E field at this point. You just enhance absorption of this active material, then they can emit more power. Okay, so there's no contradictory. It's quite different from the traditional way. Because traditional antenna, you should retrieve the source in very fundamental level. This active material, it can be a source here. Because this expression J is just a J omega mu. Mu is a dipole momentum. Okay, once this material are polarized, they have absorbed the EM wave radiative field. Okay, this is active material here. Okay, so this is quite different from the. So for classical antenna, okay, you do the Yagiuda. Okay, you use to do some fading. Okay, okay, you can increase the directivity. You can increase the directivity, but you cannot increase the emission power because the emission power has limited by the input power. Okay, except you can increase the E field at this active source region, and this active source also can produce more EM radiation when your E field is enhanced. Okay, so I have clarified this program. Okay, so this is quite different. Okay, but for this optical regime, when you put the molecule, atom, quantum dot, these are source. These are just emit. When you increase E field at this point, they just enhance the emission. Okay, so this is quite different.
So we were talking about we were putting another new species into the blue color region, right?
What's the this?
Blue color.
What's the blue color?
We use a dual hand.
This is a atom molecule
right.
quantum dot.
Existing before you consider this material, atom molecule or quantum dot, you already have a system. In this system, you have dipole.
Yes.
Yet you actually in this system you artificially add the metal sphere.
Yeah, to enhance.
This is to enhance the existing dipole. Yes, as a background. Now you put extra atoms or molecule.
Yeah. No. This atom molecule is just dipole source. Okay, no. Just dipole source. No, this is dipole source. It will emit electromagnetic waves.
It's okay. I mean, I'm not saying that your source there is not a dipole. I'm okay that it's a dipole, but existing in the system is already a dipole, as you have drawn at the beginning, which will interact with the metal sphere.
Yes.
And have some background scattering, whatever it is.
Yes.
And then now you put a particle, molecule, or quantum dot into the system.
Yeah.
And then see how strong or how weak or how the change of the dipole from this additional quantum dot. Is that right?
Yes.
You can find. But definitely, if that is the case, then whatever, if you can observe a strengthened, reinforced electromagnetic wave from this quantum dot, then I'm not surprised of this because your quantum dot puts into a system which already have some, background field which can interact with your quantum dot and make your quantum dot become stronger.
Yes.
So why it becomes a controversial?
Because there's some people work in the microwave regime. This is quite different. I give you an example. Okay. Controversial is here. If I use PEC, I put dipole here. Okay, I put dipole. This dipole is a classical dipole. I assume this distance is lambda of 4. So from here, they're in phase. They can increase the E field at this point. They can increase the E field at this point, but they do not increase the radiation power. They just change the directivity.
Oh, but that is
okay. This is quite different. Okay, I just argue that this is quite different because at this point it's not source. It's not source.
But your dipole is a dipole.
This dipole is source. It's
It's
an active material.
Exactly.
Right. This is also called dipole. We call dipole antenna. Okay. We call dipole antenna. So the contribution has induced PEC. They from here, they go back here, they are enhanced. They are double the field at this point. They just change the directivity. They do not change the output power. Because the source in microwave, they just go to a network. This is active material. You should increase field at here. They can increase. This is the equation.
Let me give you one more explanation for this. Actually, what you draw about the microwave structure is just like the LED. We add an outside coupling structure, for example, which cannot change the overall emission, but we direct the emission.
Yeah. They just change the angular response. But LED is different because active material here. If you put something can affect this material, affect this local density state or green function here, they also can change the spontaneous emission. This is quite different. Okay. If this structure can change the local density state or green function within the material's location, it also can change this.
Yeah, that's possible.
Right. But for microwave, the source, it's just very, very far from this antenna. This is source. Okay. So you cannot change. So this is quite different. This is an optical regime.
Oh, but if that's true, we go back to the previous picture. Indeed, you don't need to have an atom molecule or quantum dots, because as you know, the Purcell effects.
Yeah.
They actually, if you can enhance the spontaneous emissions inside the structure, which actually enhance the overall,
Yeah, Purcell effect this is just Purcell effect because green function change. Because this emitted part green function change. The emitted part green function initially you put in free space, this is free space green function. But you put some cavity, put some inhomogeneous environment, you change another green function.
Yes.
This enhancement we call it Purcell effect. They can enhance the spontaneous emission.
Yes, that's right. But in that case, we actually did not require quantum dot. We do not require atoms, we do not require this. We just, make the structure that actually enhance the spontaneous emission, the radiative decay rate.
Yeah.
But that is not they don't require, which can affect the non-radiative decay rate and therefore enhance the internal thermal efficiency. This does not require any active quantum dot material.
No. They should have some material to emit the wave. The vacuum they cannot emit the wave.
Yeah, the original material is already, as you draw there, is already emitting.
What's the original material?
Yeah, you can see the black dipole that you draw.
The black dipole? Yeah, this material
is already a dipole there.
No. This dipole just atom molecule. Sorry.
The black color dipole is already the atom molecule.
Yeah.
Oh, okay. So you are not adding extra dot?
No.
Okay, I see.
Not anything. This is why I clarify this. Because in last lecture, the student asked me a question how it can happen. Okay, because this active material is different. It enhances the field. Okay, so in last lecture, I talked about this Hamiltonian system. This is a classical picture. Okay, they have some contribution. They cannot explain why because from classical theory, the radiative will come to rest. Okay, so people use quantum theory to explain that. Okay, to balance. Okay, so before we talk about the fully quantum mechanical approach, I like to talk about the semi-classical picture. Okay. Before I talk about quantization Maxwell equation, I talk about semi-classical. Okay. Semi-classical picture, means what's the semi-classical? One is light intensity still strong. Light intensity is as a significance. Significant. Okay. Then object size is very small. Okay. So this part we use the Schrodinger equation. This part we just use classical Maxwell equation. This is still classical. So we call it a semi-classical picture. Okay, called semi-classical picture. Just laser. Use a laser to excite some quantum dots. We use this framework. Because laser intensity is strong, and quantum dot is very small. Because semi-classical. Okay. But if in vacuum, everything are dark, the atoms still emit light, which will be quantization of Maxwell equation. Okay, there's no choice. Okay. So let me to show this. Okay, this is everyone should know this equation. This equation is very simple. We assume it's Hamiltonian. What's a Hamiltonian? Hamiltonian is just total energy of this system. For a sphere, we go down to the ground. The kinetic energy will increase. This is zero potential line, zero potential. The potential will decrease. So this is the kinetic energy. This is the potential energy. The put them together is total energy. It's a Hamiltonian. Okay, it's a Hamiltonian. The minus, because the kinetic will increase, the potential will decrease. Add them together is conserved. Now every time the total energy, every time you the time evolution or the process, the energy will conserve. So Hamiltonian system is for any system that has conserved energy. We can construct this Hamiltonian. If we construct this Hamiltonian, we can know this governing equation very easily. Okay, it just follow this relation. I mean dp or dr equal to partial h or partial r is minus. But dr or dt is a positive partial h partial p. You can see here, p and r is two independent variables. I change the position. This r is p is negative to positive. This is just called a Hamiltonian equation. Okay, you can verify. And the dp over dt we know is equal to f. The right hand side, the minus partial h partial r, you can see it's just mg. It's just mg. Okay, this is the first equation. The second equation, dr over dt, everyone know equal to v. Okay, this is velocity. And the partial h partial p here is just p. It's just 2p over 2m. The p over m is m. Okay, you can verify. This is called a Hamiltonian equation. I talked about this in last lecture, but it's too mathematical. Maybe you cannot. I'll give you an assignment to let you derive one Hamiltonian. Okay, you can try derive. Okay, but here I just move faster. Okay, you can see for EM, also the Hamiltonian equation is also set. For EM, we know the total stored energy is 1 over 2 epsilon E squared plus 1 over mu H squared. Right, this is the total stored energy in electromagnetic system. Okay, so this EM just wise, I just choose electrical flux. I use electrical flux, okay, and then I use a vector potential. I use vector potential, then to denote the B field in here. Okay, I use the same trick. Okay, I see that Y is a momentum. I see that A is a coordinate. So everything are just a manager. The satisfy same relationship. Then I do some a little bit mathematical derivation. You'll find that I return back to Maxwell equation here. Okay, it's just a partial d partial t equals to delta h equals to delta cross a here. Use the variational principle. Okay, here it's just E equal to minus a or minus t. This is a vector potential form. Okay, this is for Coulomb gauge. So everything I said.
So it means the Hamiltonian that you describe can also be.
Yeah, use the Hamiltonian. Use the Hamiltonian equation. We can get the governing equation. This is logic. First, we know the total energy of the system. I write this equation. Then I use this Hamiltonian equation. Can get this governing equation. This is logic. This is logic. Okay.
The governing equation is Maxwell.
Yeah, you can see here. This is the first equation. Just delta. Yeah, this is Maxwell. I just use A field. The delta equals to B. The B equals to delta cross A. Okay. This is just Maxwell equation. I finished this part in next. Okay. In last lecture, I also tried to talk about the Schrodinger equation. Okay. This Schrodinger equation is very interesting. This equation is a Schrodinger guess. Schrodinger guess this equation. Okay. Schrodinger cannot verify this equation. Okay. This equation I like to talk about is phi. The phi is a wave function. This is a complex. It's a complex value. Okay. This is a very famous experiment. Okay. This is a screen. They have two slots. Okay. If you shine the light, go to the slot. They have the screen above. This is behind this screen. You can see some interference pattern. This is for optics. But for electron, it's the same. You have some filament. You heat up the electron randomly. move randomly. They can go here, they also can go here, okay? They can go a different direction. We call this wave function is phi 1. This wave function is phi 2. So finally, they get this something like this. This is the final wave function, f. It's a superposition of these two wave functions. The wave function is a complex number, so they can interference. So finally, if I put a screen after this screen, okay, you can see some interference pattern. If a long time, because each time they has an electron, okay, they randomly, you don't know. Maybe go here, they have some probability. You don't know, okay, you don't know. But if you use eye, you use your eye to see this, you know, okay, it's similar to measurement. You see this, it's similar to measurement. Okay, so go here. So above this, behind this screen, you see some interference pattern. Because the phi is a complex number, they have phase amplitude. Or this is C1 and C2 is a probability. And they specify the C1 square plus C2 square equal to 1. Okay, equal to 1. This is a very famous, okay, experiment.
You are talking about you have a general electromagnetic wave.
No electromagnetic wave. It's electron. Just heat up some filament. They can emit electron. Okay. Electron randomly. You can go this screen or go another cut. You don't know. But at longer time, you see some interference pattern. Okay. So this is due to the interference between the wave function, because the wave function is a complex value. Okay.
So we talk about the atom also wave behavior.
Yes. So the electron also similar to wave. So you can say this is a Schrodinger equation. Schrodinger equation is nothing but also a Hamiltonian. You can say this is kinetic energy, this is a potential energy. Everything that just change the P. P is originally classical equal to mv, right? The P square equals 2m. This is kinetic energy, this is potential energy. So they change the P's operator. This is quantization. Okay, P go to here. This is just Schrodinger equation. Okay, that's Schrodinger equation. If I use this eigen solution, this is plane wave. Okay, this is plane wave, IKR minus omega t. If I assume that this is a eigen solution, I just draw this Schrodinger equation. V phi equals to I partial t. This is Schrodinger equation. Let me show this de Broglie and Einstein hypothesis. Okay, why Schrodinger can use this hypothesis to guess this equation, to obtain this equation? Okay. You know de Broglie, this PhD thesis is only 3 pages. Okay, I just show this H bar. Okay. So if I know that P equal to H bar K and E equal to H bar omega, okay. You can see what happened in Schrodinger equation. Because the K is a wave vector, is also related to momentum equal to H bar, and omega also relates to energy. You see what happened in Schrodinger equation. The K dot R minus omega t here. If I substitute to this Schrodinger equation, what happened? So in the right hand side, this I H bar, sorry. In the right hand side, we get this I H bar. I H bar, because it's a partial t here, right? So it's just I omega. Okay. Then multiply. I call this maybe some F R T. Say F R T. This F R T. This is right hand side. So here it's just E. Okay, just E. This is a guess. Well, why they have H bar omega? Because due to this relation. Okay, how about this? This part. It's minus H bar 2m. They have Laplacian operator gradient. So here it's just IK squared. So it's just H bar squared, K squared, 2m, just P squared, 2m. This is origin why they can guess this equation. You can see this part is because it's partial t here. Okay. Initially I know the guess is wave form, it's similar to photon, okay, IKR omega t. So electron is also similar to photon, they have interference or wave nature. Okay. So they guess they have I omega bar, H bar here. This partial T is minus I omega. So they get H bar omega equal to E. Okay. This is a founding first. This is a founding first. Okay. Then there has another constant H bar squared over 2m. Then is IK in here, the IK squared. Okay. Then finally, you do some simplification. H bar squared, K squared, 2m. It's like P squared over 2m. Okay. So P squared 2m plus V just classical. Okay. But this is again, why it has some constant? Why Schrodinger can add this constant due to this? This can be do an experiment. Why? Because they see some spectral line from atom. They said that the spectral line are not continuous, but discrete. They found the minimum discrete is just H bar. Okay, just proportion to H bar, similar to that. They have found this phenomenon.
You are talking about some people who guess this form.
Yeah.
But not Schrodinger himself. Right?
Schrodinger invent this equation. Why this equation just think by itself? They cannot be. This is different from Maxwell. Maxwell you can measure. If someone measure, oh, this is a charge, this is a field, or this go 1 over r square. This decay 1 over r square. So they guess this of 1 over 4 pi in so 0 q square, something like this. But Schrodinger just they guess, oh, it has a waveform. Another due to this. This is by de Broglie and Einstein. Okay, then they construct this equation. They construct this equation. This is the operator form.
So what do you want to tell students the physics here? First, you have a Hamiltonian actually is a quantum understanding.
You can see quantum mechanics.
You can use it for.
This Hamiltonian is just the same with original Hamiltonian, but the change the p to the quantized form. Okay.
That's okay. I mean.
Okay. Another, just next page. Okay. I also can return back here. Another here, because H bar now is operator, right? And the phi amplitude square, this is a probability function. This is a probability. If I do a probability to the operator, this is just expectation value. This is statistics. Okay. This is some function, this is a probability, this is expectation value. Okay. Why I do this? I also use the same original variational principle, I get a Schrodinger equation. Okay, but it has some constant again. It is due to the quantum mechanics and the quantum. Everything is same. Okay. This HQ here is a number. Okay, it's a number. It's an expectation value over energy. Okay. The original Schrodinger equation H is operator. It's just operator, just something like it's an operator. It's an operator. When you measurement, you just do the expectation value. You just do this probability function. It's a real number. Okay. So they get this governing equation. So finally, I do this. I got the governing equation for Schrodinger equation. Okay. You can get the governing equation.
That means that you can use the Hamiltonian to.
Exactly. Exactly. Okay.
The y says.
Okay.
So the semi-classical.
It's semi-classical. Hamiltonian approach still works. Hamiltonian approach still works. Okay. Okay. So then we give this another Hamiltonian. Okay. This Hamiltonian for charged particle interact with EM field. Okay. This is a V term. It's a Q phi. Okay. This is a V term. How about the kinetic term? This is a little bit weird. P minus QE. Okay. The P here is called canonical momentum. Okay, equal to mv plus qa. Okay, first we see that P minus qa, just mv. Same with original. Just 1 over mv squared plus here. Why they should use P as this variable? Because P is a conserved quantity. It's a conserved quantity. You learn the momentum conservation law, right? I teach you in this course. I said Maxwell's stress tensor go through a surface. They have two kinds of momentum. One we call this a mechanical momentum, just QE, QVB. Another just a field momentum. Okay, just field momentum. Field momentum just see a field as a particle. When the particle go to this surface, we return back to give this force. Okay, so the two momentum add them together. This is together is total momentum. Okay, the total momentum is conserved. So this total momentum similar to a canonical momentum. This is conserved quantity. Okay, only mechanical momentum. Oh, is not conserved quantity. Okay, it's not conserved. It's just similar to a momentum conservation law. So here, P equal to mv plus qa. P is canonical momentum minus qa also has a kinetic energy plus. Okay, I just draw this equation carefully. Because we know a particle, for particle, we know the Hamiltonian should 102 mv squared plus v just equal to q phi. Phi is potential. But the v is not a conserved quantity. So I change the v, mv equal to p here minus qa. Okay. This is important. The p here is canonical momentum. This is canonical momentum. Okay. So this is very similar to this momentum conservation law. Okay. So the field, the mechanical momentum just kinetic momentum. This is QE, QVB. Okay. But the field also has a momentum. What's the meaning of field momentum? Because I talked about it many times. Consider a light, because light can be seen a particle. If a particle goes to its surface, it returns back, it reflects it, the surface will move. Okay. This is field momentum. This is a particle. If light, like a particle, absorbed by the material also can move. Okay, this is a momentum transfer. If you see a light and a particle, okay, this is provided field momentum. You can see it's similar to pointing vector E cross H or C squared, similar to pointing vector. Okay, so this is a field momentum. Add them together. So QV here is a field momentum. The mv is a mechanical momentum. The P here is a canonical momentum. It's conserved. Okay. So I use this Hamiltonian something. Finally, I gave a supplementary material in lecture. It's very complicated, but finally you get these two equations. Finally, you can get this. It's very magic. You can get ma equal to force equal to QE QVB. You can get this Lorentz force. You can get this equation. Okay, use this Hamiltonian. Using some mathematical trick. Okay, so most important thing is here. Okay, this is today. Because I did not talk about mathematics. Mathematics is too complicated. But I give you an assignment about how to derive this equation. You can derive by yourself. Okay, so a Hamiltonian operator for this particle interact with the electromagnetic field in free space. Okay, if a Hamiltonian operator, I mean I change the P to the quantized form. Everything is same. You can see everything is same. About quantum mechanics, everything is same. This is classical. P equal to P just canonical P. Or here I just change to P to operator. In Schrodinger equation of same. Everything is same. This H is just particle part. Just particle part. Okay. So finally I finish all. You can see for atom-photon interaction, this is semi-classical framework. Atom-photon interaction. Okay, I finish all. The total Hamiltonian now has two parts. One is the particle part, one is EM part. Okay, electromagnetic part just electrical energy plus magnetic energy is total energy, total stored energy for electromagnetics. It's EM part. Particle part, because it's quantum mechanics, just I do the exportation value phi conjugate. This is the particle part. Add them together. Then I do the vibrational principle. First, I get the Maxwell equation. Also, I get the Schrodinger equation with vector potential. Okay. Interestingly, you use vibrational principle, you also can get this J. J we call the quantum current. Okay. What's the physical meaning? I talk about the physical meaning. It's quite important. What's the physical meaning here? This physical explanation. But this is something I want to talk about. Okay. So when the atom interacts with a pump laser, okay, this laser has a very short duration, okay. When it interacts with some laser, it will be polarized, right? When you add a laser, it will be polarized and produce quantum current or Paulisian current. You can see here, This current just produced by this atom. Okay, this wave function is this potential value. Okay, this current. Okay, they produce when you add a laser to this atom. Atom is polarized because the Gaussian equation for atom is Schrodinger equation. Okay, this Schrodinger equation that produces a quantum current. Then this quantum current will generate radiation field. Okay, so this quantum current I insert to this Maxwell equation, they have generation field. Okay, they have generation field. This is a coupling process. Okay, so there are two situations. If atom is placed at a free space, the radiation will propagation to far field. Okay, cannot return back. If atom you use laser to shine, they polarize, produce some quantum current. This quantum current also emits the electromagnetic field. The field goes to far field, cannot return back. So the influence of this field to this atom can be ignored. This situation, the atom called radiative decay. They have radiative decay. However, if atom put in a cavity, the field cannot leak it out, right? It cannot leak it out. It just reacts to this atom, okay? Reacts to this atom. Especially when the cavity frequency equal to the transition frequency, okay? So the atom just absorb the photon and emit photon. Because the emitted photon cannot go out, they will return back. This is called Rabi oscillation, okay? So Rabi oscillation just can be described by the Gamma equation I showed above, okay? So there are two situations. One is put in free space, they emit out, okay, but not return back. They have radiation decay. But if you put a cavity, the field cannot go out. They return back to the atom. Atom will excite also from ground to excite state. Then from excite state go to one photon then return back. This is repeated. This is cyclic clinically. Okay, this is cyclic clinically. Okay. But the next lecture I will repeat this part, but I want to finish. Okay, this is a very interesting calculation. You can see this is spectral. Okay, this is a pulse, or this is a pulse. You can see initially, if no radiation decay, they are oscillatory and sine wave. Okay, and sine wave. But they have radiation decay. You can see they pump, but decay faster. They go to the ground state. Okay, this is a population inversion. Okay, this is a classical picture for this. The B and A is just an occupation probability. This is a population inversion. I will talk about this later. Okay, you can see this. It's a radiation decay. It's no decay case. It's a cavity. In a cavity. Okay. So this is I will, because time is approaching. I have no time to talk about this. But in last lecture I will repeat this physical explanation again. Okay. Thank you.